June 2007, question 2 from module 4. It's a question on the gas laws, and again this is about Charles' law, which is no longer on the revised specification, but for the sake of just completeness here we're going to go through and say what do we have. So the sketch of the apparatus, what we have is we have a water bath. Okay, within that water bath then we have a capillary tube. The capillary tube is open at one end, but there's a little bead of sulfuric acid at one position. Right? Alongside that, then we have a ruler acting as the scale, and we need to measure the temperature, so we're going to put in a thermometer so that we can measure the temperature. And this is our water bath, and we could put in there also, and we're going to put a stir. Right? So we have, this is open to the air, this is our capillary tube, it's open to the air, and this then is our ruler alongside there. Okay, so we have a ruler, we have capillary tube, we've got our acid bead, we have our water bath, we have our thermometer, if we could spell thermometer, and then we have our stirrer, and we're going to heat from below. So the procedure then is to heat the water bath, stirring continuously, record a series of readings of temperature and length of air column, in regular steps. And then we're going to plot a graph of volume against temperature. Suitable graph to display the range, what I've just said there, that's going to be a graph of volume against temperature, so that will be volume in millimeters squared, temperature in degrees Celsius, and we should get a straight line with an intercept. Explain how the result obtained leads the concept of the absolute zero. Well, remember, whenever we were looking at the Kelvin temperature, the degrees Celsius temperature, sorry, then we had a graph which looks like this. Okay? In order to get an absolute temperature from that, we extrapolate back. Okay? So how does this result obtained lead to the concept of an absolute temperature? Well, when we extrapolate the straight line back to touch the x-axis, it meets at the lowest possible temperature, which is absolute zero. Okay, so it goes back until it intercepts with the x-axis, and at that point that's the lowest possible temperature, which is going to be absolute zero. We now have a question calculation. A molecule of nitrogen uses all its kinetic energy to reach a maximum height of 13.4 kilometers in the Earth's atmosphere. At ground level, the gravitational potential energy of the nitrogen molecule is to be taken at zero. By considering the conservation of energy, calculate the temperature of the gas molecule at ground level. To enable it to do this, the mass of nitrogen molecule is 4.65 times 10 to the minus 6. Assume the acceleration of free fall is constant over the height involved. So we're saying here that the PE gained is equal to the KE lost, and because this is a gas molecule, its kinetic energy then is going to be equal to 3 over 2 KT, and that has to be equal to M times G times H. So fill in the values. So we have 4.65 times 10 to the minus 26 for the mass, times 9.81 for gravity, times the height that it gained, and what was the height that it reached? 13.4 times 10 to the power of 3 is equal to 3 over 2 times, and then that's 1.38 times 10 to the minus 23 times the temperature in Kelvin. So T is equal to 4.65 times 10 to the minus 26 times 9.81 times 13.4 times 10 to the 3 times 2 divided by 3 times 1.38 times 10 to the minus 23, 10 times 10 to the minus 23. So that gives, put that into your calculator, and that gives 295.3 Kelvin. So 295.3 Kelvin is the temperature that is required in order to give a kinetic energy of 3 over 2 times 1.38 times 10 to the minus 23 times 295, which is equivalent to the potential energy gained by the molecule as it moves up.